Hello everybody, welcome back to another lesson on sequences and series. Today we are going to be looking at infinite series. Before I get to the theory portion of today's lesson, I'm going to ask you a question. Have you ever thought about if there's a possibility of adding an infinite amount of terms in a pattern together? So if there's a pattern that goes on and on and on, it's just a pattern that's an infinite amount of terms, what would actually happen if I added those values together, and would it be possible to actually say if I add an infinite amount together, it's going to be equal to one specific number? Well, today we're going to have a look at that. It may not seem possible, but it's possible. We're going to do it together. Let's look at the next slide. So for today, we are going to first look at the concept of a series that diverges and a series that converges. Using that information, we're going to make a conclusion about what type of series I'm allowed to calculate a sum to infinity to. So let's have a look at the first definition, which is a series that converges, or a series that converge. When a series converges, so this word is important, it means that the terms approach zero. So as the terms of the pattern go on and on, they get closer and closer to zero. And a series that converges, the sum approaches a specific number. So the terms themselves become smaller and smaller and closer to zero, and the series of this convergent pattern approaches a specific number. So let's look at how I could actually try and illustrate that. So if I give you a specific geometric sequence where A is 2 and R is a half, so I've given you that the first term is 2 and the ratio is a half. The sequence will go in the following manner. It's going to go 2, 1, a half, a quarter, an eighth, a 16th, 1 over 32, 1 over 64. I'm sure that everyone is agreeing with me that these fractions are getting smaller and smaller. We know that nobody wants 1/64th of a cake. We want half a cake or a quarter of a cake. If I then come and say you're going to have 1 over 28th of a cake, no one's going to be happy with that. But if these fractions continue on and on, they're going to get closer to zero. So we can see that the fractions are becoming increasingly smaller, so we can say that the terms of the sequence are approaching zero. So using this same example, we know that the series is when I add the values of a sequence together. So the series will be 2 plus 1 plus a half plus a quarter going on. So just a reminder, we said that a series that is convergent, the terms itself get closer and closer to zero, but the sum approaches a certain number. So if I take the first few terms and I add 2 plus 1 plus a half plus a quarter, I get 3,75. So I can kind of see that this number is fairly close to 4. But now I'm going to see what happens if I continue to add terms of this specific sequence together. Then if I add a few more portions of this series together, with 2 plus 1 plus a half going the whole way up to a 16th, I get 3,9375. So I'm sure that you guys can see that actually the sum of this series is starting to head towards the number 4. Let's add the values from 2 going the whole way up to 1 over 64. If I added all of those together, you can test it on your calculators, I'm going to get 3,984375. I'm sure that you guys will all agree with me that this sum is approaching the value of 4. So everyone, as the terms themselves, as they went on and on and on, the terms became closer and closer to zero. But the sum of these terms continue to become closer and closer to 4. Because these two properties have been met, we can say that the series is converging. Let's look what a diverging series is. So, series that diverge. When a series diverges, it means that their terms do not approach 0 and their sum does not approach a specific number. So it's essentially the complete opposite of a series that converges. So an example of a series that diverges, if you are given the series Tn is equal to 2n plus 1, the series, or the sequence rather, will be 3, 5, 7, going on, and I'm sure you guys can see that the numbers are getting bigger. They're not getting smaller, so the terms are not approaching 0. Whereas the example before, the terms were approaching 0. The series would be 3 plus 5 plus 7 going the whole way up to plus 15. This sum is not approaching a specific example or a specific number. Before, our series was approaching the number 4. So, everybody, I hope that you can see, because the term values are not approaching 0 and that the sum is not approaching a specific number, this series is diverging. Let's look at the next slide. Please, can you just note, the next example is essentially saying that if we have a ratio that's less than -1 or a ratio that's bigger than 1, the series will diverge. In the next example, we can see that if A is 2 and if R is -3, the sequence will be 2, -6, 18, -54, going on. Again, the terms are not approaching 0. The series would be 2 minus 6 plus 18, going the whole way up to plus 486, or minus 486. This sum is not approaching a specific number. So again, guys, because the terms are not approaching 0 and the sum is not approaching a specific number, this series is diverging. After the break, we'll define sum to infinity. Welcome back, everyone. Before the break, I defined what a convergent series is and what a divergent series is. I'm quickly just going to remind you of those definitions before I define the sum to infinity. A convergent series is where the terms of a sequence get closer and closer to having a value of 0. A convergent series always gets closer and closer to a specific number. So the terms get closer to 0 and the series gets closer to a specific number. A divergent series does the complete opposite. The terms are not getting closer and closer to 0 and the series is not approaching a specific number at all. So hopefully that will make it fairly easy to tell if a series is converging or if a series is diverging. Let's define the sum to infinity. So guys, the sum to infinity is when I have a ratio that is between -1 and 1. So it's a proper fraction and the ratio does not have a value of a 0. The terms of a sequence approach 0 and their sum does approach a finite number. So this is essentially just saying when I've got a ratio between -1 and 1, the series is convergent. So, when a series is convergent, it means that I can calculate the sum of the entire series. So that's quite cool. So if my ratio is a proper fraction, I can calculate the sum of the entire series. So this means that when I can calculate the sum of a series with an infinite number of terms, as it is moving towards one finite number. So guys, I hope that you've clicked that the reason why I can do it is because the series is moving towards one specific number. So that's why I can calculate the sum of infinite terms, because convergent series have terms when added together that converge towards one number. Let's see how we're going to get the formula for this. So what I have on the board is our good old geometric series formula. But now we're going to see what actually happens if r is a proper fraction and when r to infinity is approaching 0. So essentially all that this means is that the terms with this ratio are getting closer and closer to 0. So the sum to infinity will be equal to a r to infinity, because remember I'm taking the sum to infinity, so the ratio to the power of infinity minus 1 over r minus 1. So guys, please remember that my ratio is a proper fraction. And if I take any proper fraction, I could take a half to the power of infinity, or I could take negative a third to the power of infinity. I'm sure that you guys will agree that as soon as I raise half to any type of power, especially if it's as large as infinity, the number itself is going to get closer and closer to 0. It's the same thing with negative a third. If I'm raising that to an incredibly large number, it's going to get closer and closer to 0. So that means that when I actually have my ratio to the power of infinity, it's getting closer and closer to 0. So the sum to infinity will be equal to a. I'm going to replace r to the power of infinity with a 0, because we know a proper fraction to the power of infinity is going to get very close to 0. Then if I fill in the rest, I'm going to have 0 minus 1 over r minus 1. So let's simplify. The sum to infinity will be equal to negative a over r minus 1. But because we don't really like having a negative in the numerator, this formula is commonly written as the sum to infinity is equal to a over 1 minus r. All that I've done is I've multiplied this by negative 1. Great, guys. Well, we know that I can write it as the same thing, because by multiplying it by negative 1, I'm going to get an answer of this. Sorry, guys, that's not right. Can I just stop it at sum to infinity is a over 1 minus r?
Okay.
Thank you.
Good luck to the ones that can.
Great, guys. So I'm sure you can see that I can calculate the sum to infinity if I have a, which is my first term, as well as my ratio, which is a proper fraction. Let's go to the next slide. So just a bit of a conclusion for what we have said. The sum to infinity can be calculated by a over 1 minus r if r is between negative 1 and 1 and r is not equal to 0. So this is your formula for the sum to infinity. Cool, so this example is asking, does the sequence 2, 8, 32, 128 converge or diverge? So we just have to remember the first property of a sequence or a series that converges is that the terms are getting closer and closer to 0. So if I look at this sequence, I've got 2, 8, 32, 128 going on, but I'm sure that everyone will agree with me that these terms are not getting closer and closer to 0. These terms are actually becoming larger and larger and larger. So that is the first property of a convergent series that this actual sequence fails to meet. So we're now going to look at the property of a convergent series getting closer and closer to a specific number. If I add the first two terms together, I'm going to get 10. If I add the first three terms together, I'm going to get 42. If I add the first four terms together, I'm going to get 170. So I'm sure that everyone agrees with me that these numbers are not getting closer and closer to a specific number. 10, 42, and 170 are not getting closer to a specific number. So because the terms are not getting closer to 0, and because their sums are not heading towards a specific number, 10, 42, and 170 are not heading towards a specific number, I can actually say that this sequence diverges. So I'm going to say the sequence diverges. Great, guys. So because it failed to meet the two properties of a convergent series, it means that this series is diverging. Let's look at the next example together. So we have been asked to determine the sum to infinity of the sequence that goes 81 minus 27 plus 9 minus 3 plus 1. The sum to infinity is immediately giving me a clue that I am looking for a ratio that is between -1 and 1. Let's look at the terms and see if there is a common ratio that I can pick up. Just a reminder, everyone, that if I want to check what my common ratio is, I can say that ratio is equal to term 2 over term 1. In this case, term 2 is -27, and I'm going to put this over term 1, which is 81. So the common ratio is -1/3. I'm also going to check this ratio just to double check that I'm happy with it. I can also check my ratio by saying term 3 over term 2, which will be equal to 9 over -27, which gives me an answer of -1/3. So, guys, what I've established is that each term has been multiplied by -1/3 to get to the next term. So, to get from 81 to -27, I've multiplied by -1/3. From -27 to 9, I've multiplied by -1/3. From 9 to -3, I've multiplied by -1/3. So we are actually going to be able to calculate the sum to infinity of this sequence because I've got a ratio that's between -1 and 1. And I can see that my common ratio is not 0. So because my ratio is -1/3, I can calculate the sum to infinity. Great, everyone. I hope that you're with me so far. So now all that I'm going to do is I'm going to make sure that I'm happy with what my A value is. I know that my common ratio is -1/3. Having my A and my R is going to allow me to substitute into the formula that's going to allow me to calculate the sum to infinity. So essentially, this formula is going to say that if I were to add an infinite amount of the terms of the pattern behind me, this sum would get closer and closer to this specific number. Let's calculate the sum to infinity together. So, for this particular example, we can see that A is 81. Why? Because this is my first term of the sequence. My common ratio, which I have calculated, is -1/3. Great. So at this point, I'm now going to substitute into my formula. So the sum to infinity will be equal to A, which is 81, over 1 minus my ratio, which is -1/3. We're now going to substitute all of this into my calculator. So the sum to infinity will be equal to 81 over 1 minus -1/3. sorry, let's get this fraction button to work. There we go, negative a third. So we can see that the sum to infinity of this particular sequence is going to get closer and closer to 60,75. So the sum to infinity is equal to 60,75. So this is the number of this sequence that the terms are going to get closer and closer and closer to. Cool, guys. I hope that everyone's comfortable with what I've done so far. For the last few minutes, I'm just going to recap what I have done, and then we will see how we're going at that point. So let's revise some definitions. So in this lesson, I've defined a series that diverges. Please remember that a series that diverges is a series where the terms are not getting closer and closer to a specific number, and the sum of the terms in the series are not getting closer to a certain number. So the terms are not getting closer to 0, and the sum is not getting closer to a specific number. A series that converges, the terms are getting closer and closer to 0, and the sum is getting closer and closer to a specific number. We've also discussed that the sum to infinity can be calculated for series that converge by using a, which is my first term, and putting that over 1 minus r. And just a reminder that my ratio has to be between -1 and 1, and r is not allowed to be equal to 0. Welcome back, everybody. Before the break, we spent some time defining convergent series, divergent series, and how I can actually calculate the sum to infinity. In this portion of the lesson, we're going to be looking at some more examples with calculating the sum to infinity, and we're going to look at how the sum to infinity can be represented using sigma. Great, so before we get going with examples, I'm just going to revise some concepts. Will you look at the board with me? So the key terms that I just want to make sure everyone is happy with: series that converge. This means that when a series converges, it means that the terms approach 0 and that their sum approaches a specific number. So this is the definition for a series that converges. Please remember that a series that diverges is the opposite. Cool? We then said that we can calculate the sum to infinity when my ratio is between -1 and 1 and r is not equal to 0. So when my ratio is between -1 and 1, the terms of the sequence approach 0 and their sum does approach a finite number. Because the sum approaches a finite number, that means that we can calculate the sum of the entire series. This means that we can calculate the sum of the series with an infinite amount of terms, as it is all moving towards one finite number. So the sum to an infinity allows me to calculate the value of a series with an infinite amount of terms. Great. Please just make sure that I can only use the sum to infinity when my ratio is between -1 and 1. Let's look at the next slide together. So, the formula for the sum to infinity can be written as the sum to infinity is equal to a over 1 minus r if my ratio is between -1 and 1 and r is not 0. So guys, just a reminder, this means that I will need my A as well as my R in order to calculate the sum to infinity. Let's look at the first example. So we haven't done one yet that's got a sigma involved, but just a reminder everyone, sigma means that it is a sum of a specific amount of terms. So this sigma is indicating that I'm going to work out the series that's starting from the first term that is going to go the whole way up to term infinity. So essentially this is an infinite series that I need to calculate the value of. So we can see that this sum has the TR of 3 times 2 over 3 to the power of r minus 1. Please remember everyone that for sigma sums, I have to calculate the value of the first 3 terms. Calculating the value of the first 3 terms will allow me to establish the value of A as well as the value of R. So I'm going to substitute in R is equal to 1, R is equal to 2, and R is equal to 3 in order to establish the first 3 terms of the sequence. So if I have 3 times 2 over 3 to the power of 1 minus 1, I'm going to be left with 3. Then for term 2, I've got 3 times 2 over 3 to the power of 2 minus 1. And everyone, that is just going to leave me with a value of 2. Cool, guys. And then to find the value of the third term, I'm going to say 3 times 2 over 3 to the power of 3 minus 1, which is 3 times 2 over 3 to the power of 2, which is the same thing as 3 times 4 over 9, which gives me 4 over 3 as an answer. So we have the first 3 terms being 3, 2, and 4 over 3. We can establish by taking our ratio as term 2 over term 1. That's going to give me an answer of 2 over 3. So the common ratio is 2 over 3 because I've been multiplying by 2 over 3 each time. A is equal to 3 as it is my first term. So the sum to infinity is equal to 3 over 1 minus 2 over 3. So all I've done is I've substituted in my A as well as my R. Let's pop this all on my calculator. Then we can actually see what the sum to infinity is. So I've got 3 over 1 minus 2 over 3, which is equal to 9. So for this specific example, the sum to infinity is equal to 9. Great, everyone. So I hope that everyone is comfortable with the example that I've done with you. We were able to calculate the sum to infinity once we had our A and once we had our R. After the break, we'll come back and we'll look at more examples of calculating the sum to infinity. See you soon. Welcome back, everyone. Before the break, we had looked at a sigma example of an infinite series. For the next portion of the lesson, I'm going to look at some other examples about calculating the sum to infinity. Please remember that I can only calculate the sum to infinity when my ratio is between -1 and 1, and when the ratio is not equal to 0. So the ratio has to be a proper fraction in order for me to calculate the sum to infinity. Let's have a look at the next example. So guys, we've been asked to consider the geometric series that goes m minus 5 plus m minus 5 squared plus m minus 5 cubed going on. A is asking me for what values of m is the series convergent. B is asking me to calculate in terms of m the sum to infinity of the series if the series is convergent. And hence, for number C, we need to calculate the sum to infinity of the series 7 minus 5 plus 7 minus 5 squared plus 7 minus 5 cubed. So let's get going with A. So we've been asked to consider this series, and we've been asked for what values of m is this series convergent. Great. Before I even start writing, please just remember that the definition of a convergent series means that the ratio has to be between -1 and 1. So what this means is that I need to first establish what the ratio is in the example behind me. Once I know what that ratio is, I'm going to isolate m in order to determine the values that m can lie between in order for the series to be convergent. So let's write down the next few steps. So if I'm going to be calculating the common ratio for this example, I need to see what has each term been multiplied by to get to the next term. So I know that I can commonly write the common ratio is equal to term 2 over term 1. Term 2 is equal to m minus 5 squared, and I'm going to put that over m minus 5. Hopefully everyone can see that m minus 5 squared over m minus 5 is equal to m minus 5. So that means for this example, my common ratio is equal to m minus 5. But I know that for the series to be convergent, the ratio has to lie between -1 and 1. So what I'm going to do is I'm going to substitute in my ratio into this middle portion so that I can isolate the values for m that this series will be convergent. So on my next line, I'm going to say that the ratio of m minus 5 has to be between -1 and 1. We want to know for what values of m is this series convergent. So in order to determine the barriers that will work, I'm going to have to add 5 to the left-hand side of the inequality. I'm also going to have to add 5 to the right-hand side of the inequality. So that means that I'm going to have 4, because -1 plus 5 is 4. And then I'm going to have 6. So this statement is saying that m has to be greater than 4 but less than 6. So that means for this series to actually be convergent, m has to be between 4 and 6. That will mean that this sum to infinity can be calculated only if m is between 4 and 6. Cool. Let's have a look at B. We are going to calculate in terms of m the sum to infinity of the series m minus 5 plus m minus 5 squared plus m minus 5 cubed going on. We've been told that we can assume that the series is convergent. Cool, guys. So just a reminder, because the series is convergent, I can calculate the sum to infinity. In order to substitute into the sum to infinity, I need to have my a present as well as my r. I want my sum to infinity in terms of m. So that means whatever our sum to infinity is, we're going to simplify it in terms of m. Let's go back to the board. Great, so I need to substitute in a. A is my first term, and I can see that m minus 5 is my first term. On the previous slide, we discussed that the common ratio is equal to m minus 5. So let's substitute in a and r. So the sum to infinity will be equal to m minus 5 over 1 minus m minus 5. So we're now going to simplify this so I can calculate the sum to infinity in terms of m. So the sum to infinity will be equal to m minus 5 over 1 minus m plus 5. Great. So if I want to conclude, I've got the sum to infinity in terms of m will be equal to m minus 5 over 6 minus m. Great, everyone. I hope that everyone's comfortable so far. This example looks slightly weird because we're used to the sum to infinity actually approaching a specific number. For this example, the sum to infinity is approaching a number, except this number has been represented in terms of m. So it looks a bit different, but we've still calculated the sum to infinity by substituting in our a value as well as our r value and making sure that it has been simplified. So my answer is in terms of m. Let's look at C together. So it says, hence, calculate the sum to infinity of the series 7 minus 5 plus 7 minus 5 squared plus 7 minus 5 cubed. So what I want everyone to do in this example is to try and see the link between what has been presented to you and what was asked. So we know the pattern was given to you as m minus 5 plus m minus 5 squared plus m minus 5 cubed. So I'm hoping that everyone can see the link. And the link is that the m has been replaced with a 7. So we've now seen that there is a connection between C and with what was asked at the beginning. For this example, m is equal to 7, and I've been asked to calculate the sum to infinity. So let's write that down. For this example, m is equal to 7. But there is a problem with m being equal to 7. What could that problem be? I'm going to give you a few seconds to think about it. Have I, in this entire example, and if you've just joined us, we've been working with m throughout this example, I put restrictions on my m value a bit earlier on in this sum. I'm going to go back to the slide where I worked out the values of m that will mean that the series is convergent. So I'm going to go back to that slide, but please keep in the back of your mind, m is equal to 7, and why could it be a problem if m is equal to 7? Let's take a look back at that slide. Cool, so I've asked you guys to keep in the back of your mind that m is equal to 7 and why that is a problem. If I go back to A, I had to determine the values of m for which the series was convergent. We then solved the inequality and saw that for the series to be convergent, m has to be between 4 and 6. So if I go back to C, I know that for this series to be convergent, m has to be between 4 and 6. And why is it important for m to be between 4 and 6? It's important because it will actually mean that this series itself converges, and I'm allowed to calculate the sum to infinity if the series converges. So I cannot calculate the sum to infinity as m is greater than 6. So that completely breaks this condition. So I hope that everyone's comfortable with what I've done. Because m is greater than the values that m is allowed to have, m is only allowed to have a value between 4 and 6, because that means that the series converges, so I can calculate the sum to infinity. Because m is greater than that, I am not allowed to calculate the sum to infinity. Let's have a look at the next example together. Great. So, just a reminder that now we are going to be using the formula for the sum to infinity of a geometric series to write down 0,8 recurring as a proper fraction. So first things first, let's write down what 0,8 recurring is. We've discussed that it's going to be 0,88888 going on. This means that I can actually write 0,8 recurring as a sum, because it's going to be 0,8 recurring is equal to 0,8 plus 0,08 plus 0,008 plus 0,0008, going on and on and on. If I want to be able to express the sum to infinity of this number, I need to establish what A is and what R is. I'm just going to have a look, and I can see that if this was a geometric series, 0,8 would be my A value. If I want to actually be able to substitute into the sum to infinity, which we know is equal to A over 1 minus R, what we're going to do is we need to actually see what the value of R is. So from 0,8 to 0,08 to 0,008, I need to establish what my common ratio is. I know that I can work out my common ratio to be term 2 over term 1. Term 2 is equal to 0,08 over term 1, which is 0,8. This is going to give me a common ratio of 0,1. So I can see that I multiply by 0,1 each time. So if I substitute into the sum to infinity formula, A is equal to 0,8. I'm then going to put this over 1 minus my ratio, which is 0,1. Let's put this into my calculator. So I'm going to have 0,8 over 1 minus 0,1. This is going to give me a final answer of 8 over 9. So the sum to infinity for 0,8 recurring can be written as 8 over 9. Wonderful, everyone. So this is not the only case where I can actually use the sum to infinity to write a recurring decimal. The biggest thing is to establish what the A is and what the A would be during the sum, and then to establish the common ratio. Because the decimal is reoccurring, it's going on an infinite basis, which means that I can calculate the sum to infinity. Great, everybody, but I really hope that you've enjoyed today's lesson. We've discussed when a series is converging and how the terms of a convergent series have to be getting closer to 0, and that the series for a convergent series has to be approaching a finite number. We've used the formula for an infinite series to calculate the sum to infinity, and hopefully these examples have helped you. Otherwise, I hope that you have a wonderful day, and I hope to see you again soon. Bye.